Chapter 1. Introduction to Quantum Physics. The Basics of Quantum Theory. Quantum theory, at its core, is a revolutionary framework that describes the fundamental behavior of matter and energy at the smallest scales. It challenges our classical intuitions about the physical world, introducing concepts such as wave-particle duality, where particles like electrons exhibit both wave-like and particle-like properties. This duality is a cornerstone of quantum mechanics, leading to the understanding that the very fabric of reality is more complex than previously imagined. One of the most intriguing aspects of quantum theory is the principle of superposition. This principle posits that particles can exist in multiple states simultaneously until they are observed or measured. Such behavior is famously illustrated by the thought experiment known as Schrödinger's cat, which presents a scenario where a cat in a sealed box is simultaneously alive and dead until someone opens the box to observe it. This idea fundamentally alters our comprehension of reality, suggesting that observation plays a critical role in shaping the universe. Entanglement is another fascinating phenomenon that emerges from quantum theory. When particles become entangled, the state of one particle instantaneously influences the state of another, regardless of the distance separating them. This has led to a re-evaluation of the concepts of locality and causality, as entangled particles seem to communicate in ways that defy traditional notions of space and time. The implications of entanglement are profound, potentially paving the way for advancements in quantum computing and secure communication. Quantum theory also introduces the concept of quantization, which states that certain properties, such as energy, can only take on discrete values rather than a continuous range. This leads to the idea of quantum states and energy levels, which explain how electrons orbit the nucleus of an atom. Understanding these quantized states is crucial for explaining a wide array of phenomena, from the colors of light emitted by atoms to the behavior of semiconductors in modern electronics. In summary, the basics of quantum theory provide a glimpse into a world that defies our everyday experiences, where particles can be in multiple states at once and can instantaneously affect one another over great distances. As we delve deeper into the quantum frontier, we uncover not just the mysteries of the universe but also the potential for transformative technologies that could reshape our future. The study of quantum theory continues to be a vibrant field of research, pushing the boundaries of what we understand about the nature of reality. Historical background and key figures. The exploration of quantum mechanics has deep roots in the early 20th century, a period marked by revolutionary advancements in physics. Pioneers such as Max Planck and Albert Einstein laid the groundwork for this intriguing field by introducing concepts that challenged classical physics. Planck's quantum hypothesis, which suggested that energy is quantized, changed the way scientists understood light and energy, while Einstein's work on the photoelectric effect provided pivotal evidence for the existence of quanta. Following these early contributions, numerous key figures emerged, each adding layers of understanding to quantum theory. Niels Bohr, for instance, introduced the Bohr model of the atom, which depicted electrons orbiting the nucleus in specific energy levels. This model not only explained the spectral lines of hydrogen but also set the stage for further developments in quantum mechanics. Additionally, figures like Werner Heisenberg and Erwin Schrödinger advanced the field with their formulation of matrix mechanics and wave mechanics, respectively, offering different perspectives on the behavior of subatomic particles. The mid-20th century saw the realization of quantum mechanics' practical applications, thanks in large part to the work of scientists like Richard Feynman and John von Neumann. Feynman's path integral formulation provided a new way to compute quantum amplitudes, while von Neumann's contributions to the mathematical foundations of quantum mechanics established a rigorous framework for its principles. These advancements not only deepened theoretical understanding but also paved the way for the burgeoning field of quantum computing. As quantum mechanics evolved, so did its implications for our understanding of the universe. The development of quantum field theory, which merges quantum mechanics with special relativity, enabled physicists to describe fundamental forces and particles in a unified manner. Key figures like Steven Weinberg and Sheldon Glashow played critical roles in formulating the standard model of particle physics, which describes the electromagnetic, weak, and strong interactions that govern the behavior of all matter. Today, the legacy of these historical figures continues to inspire new generations of scientists exploring the quantum frontier. Their groundbreaking work not only reshaped our understanding of the microworld but also opened up possibilities for innovative technologies, such as quantum computing and quantum cryptography. As we delve deeper into these mysteries, the contributions of past visionaries remain crucial in guiding our exploration of the universe's fundamental nature. The importance of quantum physics in modern science. Quantum physics stands at the forefront of modern science, revolutionizing our understanding of the universe. It delves into the behavior of matter and energy at the smallest scales, where the classical laws of physics no longer apply. This field has not only transformed theoretical physics but has also led to practical applications that impact our daily lives, from the technology in our smartphones to the functioning of medical imaging devices. One of the most significant contributions of quantum physics is the development of quantum mechanics, which provides a framework for understanding phenomena that occur at the atomic and subatomic levels. This framework has allowed scientists to explain complex behaviors that classical physics could not, such as the dual nature of light and matter. By embracing the principles of superposition and entanglement, researchers are unlocking new realms of possibilities that could redefine the limits of technology. Quantum computing is a prime example of how quantum physics is shaping the future. Unlike classical computers that use bits as the smallest unit of information, quantum computers utilize qubits, which can exist in multiple states simultaneously. This capability promises to drastically increase computational power, enabling us to solve problems that were previously deemed insurmountable, such as complex simulations in chemistry and physics that could lead to breakthroughs in material science. Furthermore, quantum physics has given rise to advancements in secure communication through quantum cryptography. By harnessing the principles of quantum mechanics, it is possible to create systems that are fundamentally secure, as any attempt to eavesdrop on quantum communications would disturb the system, alerting the parties involved. This development is crucial in an era where data privacy is paramount, and the demand for secure networks continues to grow. In conclusion, the importance of quantum physics in modern science cannot be overstated. Its principles not only enhance our understanding of the universe but also pave the way for groundbreaking technologies that have the potential to change our world. As we continue to explore the quantum frontier, we stand on the brink of new discoveries that will further illuminate the mysteries of nature and expand the horizons of human ingenuity. Chapter 2: The Nature of Reality. Wave-particle duality. Wave-particle duality is one of the most intriguing concepts in quantum mechanics, illustrating that particles, such as electrons and photons, exhibit both wave-like and particle-like properties. This duality challenges our classical understanding of physics, which categorizes entities as either waves or particles. Instead, experiments show that the behavior of these subatomic particles depends on how they are observed, leading to a fundamental question about the nature of reality itself. The phenomenon was first highlighted by Albert Einstein in his explanation of the photoelectric effect, where light appears to act as a stream of particles, or photons, when interacting with matter. Conversely, Thomas Young's double-slit experiment demonstrated that light can also behave as a wave, creating interference patterns when not observed. This dual nature is not limited to light. Electrons, which we traditionally think of as particles, also display wave-like characteristics under certain conditions. One of the most fascinating aspects of wave-particle duality is its implications for our understanding of measurement in quantum mechanics. When a particle is not being observed, it exists in a state of probability, described by a wave function. Only when a measurement is made does the wave function collapse, and the particle adopts a definite state. This raises philosophical questions about the role of the observer in defining the properties of a particle, suggesting that reality may not be as objective as we would like to believe. Further exploration of wave-particle duality has led to advancements in technology, especially in fields like quantum computing and telecommunications. Understanding how particles can exist in multiple states simultaneously has opened up new possibilities for processing and transmitting information. Quantum bits, or qubits, harness this duality to perform calculations at speeds unattainable by classical computers, potentially revolutionizing the way we handle data. In summary, wave-particle duality is not just a quirk of quantum mechanics. It fundamentally reshapes our understanding of the universe. By demonstrating that the behavior of particles is context-dependent, it prompts us to reconsider our notions of reality and observation. As we delve deeper into the quantum realm, the implications of this concept will continue to unfold, influencing both theoretical physics and practical applications in technology. The observer effect. The observer effect is a fascinating phenomenon in quantum mechanics that illustrates the complex relationship between observation and the behavior of particles. This effect suggests that the act of observing a particle can alter its state, leading to a myriad of interpretations and implications in the realm of physics. For example, when scientists attempt to measure the position of an electron, the very act of measurement can change its momentum, making it impossible to determine both with absolute certainty simultaneously. This principle challenges our understanding of reality and raises questions about the nature of existence itself. At the heart of the observer effect lies the uncertainty principle, formulated by Werner Heisenberg. This principle asserts that certain pairs of physical properties, like position and momentum, cannot be simultaneously known to arbitrary precision. As a result, the more accurately we measure one property, the less accurately we can know the other. This inherent limitation is not due to flaws in our measurement tools. Rather, it is a fundamental aspect of the quantum world, highlighting the peculiarities of subatomic particles and their interactions. The implications of the observer effect extend beyond mere theoretical constructs. They influence practical applications in technologies such as quantum computing and cryptography. In quantum computing, the ability to manipulate and measure qubits, the basic units of quantum information, relies heavily on understanding and managing the observer effect. Similarly, in quantum cryptography, the observer effect ensures secure communication as any attempt to eavesdrop on the quantum system alters its state, alerting the parties involved. Moreover, the observer effect has philosophical implications, prompting discussions about the role of consciousness in the universe. Some interpretations suggest that observation by a conscious being may be necessary for the collapse of the wave function, a process that determines the state of a quantum system. This idea blurs the lines between physics and philosophy, inviting a deeper inquiry into the nature of reality, perception, and existence. In summary, the observer effect serves as a gateway into the enigmatic world of quantum mechanics, revealing the intricate dance between observation and reality. As we delve deeper into the mysteries of the universe, understanding this phenomenon not only enhances our grasp of quantum physics but also challenges our fundamental beliefs about the nature of existence. The observer effect ultimately reminds us that our perception of reality is inextricably linked to the act of observing it, inviting us to reconsider our understanding of the universe itself. Quantum superposition. Quantum superposition is one of the most intriguing principles of quantum mechanics, capturing the imagination of scientists and enthusiasts alike. At its core, superposition refers to the ability of quantum systems to exist in multiple states simultaneously until measured. This phenomenon is starkly different from classical physics, where an object can only be in one state at any given time. The implications of superposition challenge our traditional understanding of reality and raise profound questions about the nature of existence itself. One of the most famous thought experiments illustrating quantum superposition is Schrödinger's cat. In this scenario, a cat is placed in a sealed box with a radioactive atom, which has a 50% chance of decaying and triggering a poison release. Until the box is opened and an observation is made, the cat is considered to be both alive and dead, existing in a superposition of states. This paradox highlights the counterintuitive nature of quantum mechanics and prompts further exploration into the relationship between observation and reality. In practical terms, superposition is a fundamental principle behind quantum computing. Unlike classical bits, which can be either 0 or 1, quantum bits or qubits can represent both at the same time. This ability to perform multiple calculations simultaneously allows quantum computers to solve complex problems much faster than their classical counterparts. As researchers continue to develop quantum technologies, the concept of superposition remains a critical element in advancing the field of computation. The phenomenon of quantum superposition does not only pertain to particles and computing. It plays a significant role in various technologies, including quantum cryptography and quantum teleportation. These applications harness the principles of superposition and entanglement to create secure communication systems and transfer information instantaneously across distances. Such advancements could revolutionize the way we transmit data, creating a new frontier in technology and security. As we delve deeper into the mysteries of quantum mechanics, the concept of superposition invites us to reconsider our understanding of reality and the universe. It challenges the boundaries of what we perceive as possible and opens new pathways for scientific exploration. The ongoing research into quantum phenomena not only enhances our technological capabilities but also enriches our philosophical perspectives about the nature of existence and the universe itself. Chapter 3: The Quantum World. Atoms and subatomic particles. Atoms are the fundamental building blocks of matter, composed of a nucleus surrounded by a cloud of electrons. The nucleus contains protons and neutrons, which are themselves made up of even smaller particles called quarks. This intricate structure forms the basis of everything we see, touch, and experience in our universe. Understanding atoms is essential for grasping the principles of chemistry and physics, as they dictate the properties and behaviors of all substances. Electrons, while tiny compared to protons and neutrons, play a crucial role in defining the chemical characteristics of an element. They exist in various energy levels or shells around the nucleus and can move between these levels by absorbing or releasing energy. This movement is fundamental to the formation of chemical bonds, which occurs when atoms share or transfer electrons, leading to the creation of molecules. Subatomic particles are not merely passive components of atoms, they exhibit wave-particle duality, a principle central to quantum mechanics. This means that particles such as electrons can behave both as particles and as waves, depending on how they are observed. This duality challenges our conventional understandings of physics and illustrates the complexities of the quantum world, where certainty gives way to probabilities. Moreover, the interactions between subatomic particles are governed by the four fundamental forces: gravitational, electromagnetic, weak nuclear, and strong nuclear forces. These forces dictate how particles interact with one another, leading to the stability of atoms and the formation of larger structures. Understanding these forces is key to unlocking the mysteries of the universe, as they influence everything from the behavior of galaxies to the formation of atoms. As we delve deeper into the realm of subatomic particles, we uncover the nuances of their behaviors and interactions, which are essential for advancements in technology and our understanding of the cosmos. Research in particle physics continues to reveal new insights, pushing the boundaries of what we know about matter and energy. The quest to understand atoms and their components is not just an academic pursuit, it is a journey that could redefine our comprehension of reality itself. Quantum states and their properties. Quantum states are fundamental concepts in quantum mechanics that describe the unique conditions of particles at the quantum level. Unlike classical states, which can be precisely defined, quantum states can exist in multiple configurations simultaneously due to the principle of superposition. This means that a particle, such as an electron, can be in various energy levels or locations at the same time until it is measured. Understanding quantum states is crucial for grasping the behavior of matter and energy in the universe. One of the remarkable properties of quantum states is entanglement, where two or more particles become interconnected in such a way that the state of one particle instantly influences the state of another, regardless of the distance separating them. This phenomenon challenges our classical intuitions about separability and locality. Entangled particles can exhibit correlations that are stronger than anything predicted by classical physics, suggesting a deep and intrinsic connection between them that defies conventional understanding. Quantum states also have associated probabilities, which are fundamentally different from classical certainty. When a quantum system is observed, it collapses from a superposition of states into one observable state, a process known as wave function collapse. The probability of obtaining a particular state can be calculated using a mathematical function called a wave function, which encodes all the possible configurations of the system. This probabilistic nature of quantum mechanics introduces a level of uncertainty that is intrinsic to the behavior of particles at the quantum level. The manipulation of quantum states has led to revolutionary advancements in technology, notably in the field of quantum computing. By harnessing the properties of superposition and entanglement, quantum computers can perform calculations at speeds unimaginable with classical computers. This capability opens up new horizons for solving complex problems in fields such as cryptography, materials science, and drug discovery, illustrating the profound impact of quantum mechanics on our technological landscape. In summary, quantum states and their properties challenge our conventional understanding of physics and reality. They embody the strange behaviors of particles that exist in a realm governed by uncertainty and interconnectedness. As we delve deeper into this quantum frontier, we unlock new possibilities that can reshape our understanding of the universe and propel us into an era of unprecedented technological advancement. Entanglement and non-locality. Entanglement and non-locality are two of the most intriguing phenomena in quantum mechanics, challenging our classical intuitions about the nature of reality. When particles become entangled, their quantum states become linked in such a way that the state of one particle instantly influences the state of another, regardless of the distance separating them. This phenomenon has been famously illustrated by the thought experiment known as Schrödinger's cat, where a cat in a box can be simultaneously alive and dead until observed, reflecting the peculiarities of quantum states. The implications of entanglement stretch far beyond theoretical musings. They have practical applications in the emerging field of quantum computing, where entangled qubits can perform calculations at speeds unattainable by classical computers. This interconnectedness of qubits allows for phenomena such as superposition and interference, which are harnessed to solve complex problems more efficiently. As researchers explore the potential of quantum technologies, entanglement stands at the forefront of innovation. Non-locality, the ability of entangled particles to affect each other instantaneously over vast distances, raises profound questions about the nature of space and time. This phenomenon suggests that information can be transmitted faster than the speed of light, defying Einstein's theory of relativity. Experiments such as those conducted by Alain Aspect in the 1980s have provided strong evidence for non-locality, demonstrating that entangled particles behave as if they are connected in ways that challenge our conventional understanding of causality. Critics of quantum mechanics have long debated the implications of entanglement and non-locality, arguing that they undermine the principle of locality, which states that objects are only directly influenced by their immediate surroundings. However, proponents argue that these phenomena do not violate locality but rather indicate a deeper, more complex structure of reality. As scientists continue to investigate the nuances of these concepts, they inch closer to a unified theory that may reconcile quantum mechanics with general relativity. In summary, entanglement and non-locality are not merely abstract concepts but pivotal elements of quantum mechanics that hold the key to future technological advancements. As our understanding of these phenomena deepens, we unlock new possibilities in communication, computation, and our fundamental understanding of the universe. The mysteries of entanglement continue to inspire curiosity and innovation in the scientific community, paving the way for a new era of exploration in the quantum frontier. Chapter 4: Quantum Mechanics in Action. Quantum Computing. Quantum computing represents a revolutionary leap in the realm of technology, harnessing the principles of quantum mechanics to process information in fundamentally different ways than traditional computers. At its core, quantum computing exploits the behaviors of subatomic particles, utilizing qubits instead of classical bits. While a standard bit can exist in one of two states, 0 or 1, a qubit can exist simultaneously in multiple states due to a property known as superposition. This allows quantum computers to perform complex calculations at speeds unattainable by their classical counterparts. One of the most exciting aspects of quantum computing is its potential to solve problems that are currently intractable for traditional systems. For instance, quantum computers could revolutionize fields such as cryptography, drug discovery, and optimization problems, providing solutions to challenges that have long stymied researchers and industry experts. Algorithms specifically designed for quantum computers, such as Schia's algorithm, demonstrate the power of quantum processing by efficiently factoring large numbers, a task that is exceedingly difficult for classical computers. Moreover, the phenomenon of entanglement, another cornerstone of quantum mechanics, plays a crucial role in the effectiveness of quantum computers. When qubits become entangled, the state of one qubit can depend on the state of another, regardless of the distance separating them. This interconnectedness can significantly enhance the processing capabilities of quantum systems, enabling them to perform parallel computations in ways that classical systems cannot. Despite the promise that quantum computing holds, significant challenges remain in its development. Building a scalable quantum computer involves overcoming issues related to qubit coherence and error rates, as environmental factors can easily disrupt quantum states. Researchers worldwide are actively exploring various technologies, such as superconducting qubits and trapped ions, in a quest to develop robust quantum computing systems that can reliably outperform classical technology. In conclusion, quantum computing is not merely a technological advancement, it represents a paradigm shift in our understanding of computation itself. As researchers continue to unlock the mysteries of quantum mechanics and refine the practical applications of quantum computing, we stand on the brink of a new era in science and technology. The implications of this revolutionary technology could reshape entire industries and fundamentally alter our approach to problem-solving across the globe. Quantum cryptography. Quantum cryptography represents a groundbreaking intersection of quantum mechanics and information security, aiming to revolutionize how we protect data. At its core, it leveraged the principles of quantum physics to create secure communication channels, harnessing the peculiar behaviors of quantum particles. Unlike traditional cryptography, which relies on complex algorithms, quantum cryptography ensures security through the laws of physics, making eavesdropping detectable and thus unfeasible. One of the most notable applications of quantum cryptography is quantum key distribution, QKD. This technique allows two parties to generate a shared, secret random key, which can then be used to encrypt and decrypt messages. What makes QKD particularly fascinating is its reliance on quantum entanglement and superposition, where the act of measuring a quantum state inevitably alters it. This principle ensures that any attempt to intercept the key will introduce detectable anomalies in the communication, alerting the parties involved. In recent years, advancements in technology have led to the development of practical quantum cryptography systems. Various research institutions and companies are actively working on creating robust QKD networks, with some cities already testing these systems for secure communication. As quantum technology progresses, the potential for widespread implementation grows, offering a glimpse into a future where secure data transmission is not only possible but commonplace. However, the transition to quantum cryptography is not without its challenges. The infrastructure required for implementing QKD on a large scale is complex and costly, necessitating significant investment in research and development. Additionally, there are concerns about the integration of these systems with existing technologies and how they will coexist with classical cryptographic methods. Despite these hurdles, the promise of quantum cryptography is immense. As cyber threats continue to evolve, the need for more secure communication methods becomes increasingly critical. Quantum cryptography holds the key to protecting sensitive information in an age where data breaches are rampant, paving the way for a future where privacy and security are paramount in our interconnected world. Applications in medicine. The field of medicine is undergoing a revolutionary transformation thanks to the principles of quantum mechanics. Quantum technologies are being explored for their potential applications in diagnostics, treatments, and the understanding of complex biological systems. One of the most promising areas is quantum imaging, which enables the development of highly sensitive imaging techniques that can detect diseases at much earlier stages than conventional methods, thus improving patient outcomes significantly. Moreover, quantum computing holds the key to analyzing vast amounts of medical data more efficiently than classical computers. By leveraging quantum algorithms, researchers can model complex biological processes and drug interactions with unprecedented precision. This could lead to the discovery of new treatments and personalized medicine strategies, tailored specifically to the genetic makeup of individual patients, enhancing the efficacy of therapies. In addition to diagnostics and treatment, quantum technologies also offer advancements in medical devices. For instance, quantum sensors can measure physiological parameters with incredible accuracy, allowing for real-time monitoring of patients. This paves the way for innovations in wearable technology that can provide continuous health assessments, thereby empowering patients and healthcare providers to make informed decisions based on reliable data. The integration of quantum mechanics in medicine also extends to the field of mental health. Quantum theories are being investigated to understand the cognitive processes and neural behaviors that underpin mental disorders. By applying quantum principles to neuroscience, scientists hope to identify novel therapeutic approaches that could potentially revolutionize the treatment of mental health conditions, which have long been challenging to address with traditional methods. As we stand on the cusp of these advancements, the future of medicine appears to be intertwined with the quantum realm. While challenges remain in translating quantum theories into practical applications, the potential benefits are vast. From early disease detection to personalized therapies and enhanced medical devices, the applications of quantum mechanics in medicine promise to redefine our approach to healthcare and improve the quality of life for countless individuals. Chapter 5. The Role of Quantum Physics in Cosmology. The Big Bang Theory. The Big Bang Theory stands as one of the most significant scientific concepts explaining the origin and evolution of the universe. This theory posits that approximately 13.8 billion years ago, the universe began as an incredibly hot and dense point, often described as a singularity. From this initial state, the universe began to expand rapidly, a process that continues today, leading to the vast cosmos we observe. The evidence supporting this theory is compelling, including the cosmic microwave background radiation, which serves as a remnant of the early universe, and the observable redshift of distant galaxies, indicating their ongoing movement away from us. One of the key aspects of the Big Bang theory is the concept of cosmic inflation. This theory suggests that in the first few moments after the Big Bang, the universe underwent an exponential expansion, growing from subatomic scales to the size of a grapefruit almost instantaneously. This rapid expansion helps to explain the uniformity of the cosmic microwave background radiation and the large-scale structure of the universe. It also addresses some of the major questions about the distribution of galaxies and the overall geometry of the cosmos. As scientists delve deeper into the implications of the Big Bang theory, they examine how it intersects with other fundamental concepts in physics, such as quantum mechanics and general relativity. The quest to unify these theories has led to exciting developments in theoretical physics, including string theory and the multiverse hypothesis. These ideas suggest that our universe may be just one of many, each with its own unique properties and laws of physics, challenging our understanding of reality itself. Moreover, the Big Bang theory has profound implications for our understanding of time and space. It posits that time itself began with the Big Bang, reshaping our perceptions of past, present, and future. This notion invites philosophical inquiries about the nature of existence and the directionality of time, prompting reflections on whether the universe is destined for a continuation of expansion or if it might eventually collapse in a big crunch. Such questions not only pique our scientific interest but also engage our imagination about the future of the cosmos. In conclusion, the Big Bang theory remains a cornerstone of modern cosmology, providing a framework for understanding the universe's origins and its ongoing evolution. As research continues, new discoveries related to dark matter, dark energy, and the fundamental forces of nature promise to further refine our understanding of the universe. The journey to comprehend our cosmic beginnings is a testament to human curiosity and the relentless pursuit of knowledge, inviting us to ponder our place in the grand tapestry of existence. Dark matter and dark energy. Dark matter and dark energy are two of the most intriguing components of our universe, making up approximately 95% of its total mass-energy content. Dark matter, which does not emit, absorb, or reflect light, is thought to be responsible for the gravitational forces that govern the motion of galaxies and galaxy clusters. Despite its elusive nature, scientists infer its existence through its gravitational effects on visible matter, leading to the conclusion that it plays a crucial role in the structure of the cosmos. In contrast, dark energy is an even more mysterious force that is believed to be driving the accelerated expansion of the universe. While dark matter acts as an attractive force, dark energy exerts a repulsive effect, counteracting the gravitational pull of matter. This phenomenon was first discovered in the late 1990s when astronomers observed that distant supernovae were fainter than expected, indicating that the universe's expansion is speeding up rather than slowing down. The relationship between dark matter and dark energy remains a subject of intense research and debate among physicists. Some theories suggest that these two mysterious components may be interconnected, with dark energy potentially arising from the properties of dark matter itself. This has led to various hypotheses, including the possibility of modifications to our understanding of gravity, which may help to unify these two distinct aspects of the universe. As scientists continue to explore the nature of dark matter and dark energy, advanced observational techniques and experiments are being developed. Projects such as the Large Hadron Collider and various space telescopes aim to uncover more about these cosmic enigmas. The search for dark matter particles and the study of cosmic microwave background radiation are pivotal in piecing together the puzzle of the universe's composition and fate. Understanding dark matter and dark energy is essential for a comprehensive grasp of the cosmos. Not only do they challenge our fundamental knowledge of physics, but they also inspire new theories and technologies that could reshape our understanding of the universe. As research progresses, the mysteries surrounding these phenomena may eventually reveal profound insights into the nature of reality itself. Quantum fluctuations in the early universe. Quantum fluctuations are a fundamental aspect of quantum mechanics, representing temporary changes in energy levels within a point in space. In the context of the early universe, these fluctuations played a crucial role in shaping the cosmic landscape. Shortly after the Big Bang, the universe was an incredibly hot and dense environment, where quantum mechanics govern the behavior of particles. As the universe expanded and cooled, these fluctuations became imprinted onto the fabric of spacetime, leading to the large-scale structure we observe today. One of the most significant impacts of quantum fluctuations was their influence on the distribution of matter in the universe. As regions of space experienced different energy levels, some areas became slightly denser than others. This uneven distribution of matter eventually led to the formation of galaxies, stars, and other cosmic structures. The seeds of these structures were sown in the chaotic quantum realm, illustrating how the microscopic world can have profound implications on the macroscopic universe. The study of quantum fluctuations also provides insight into the nature of dark matter and dark energy, which together comprise most of the universe's mass-energy content. The fluctuations may have contributed to the formation of dark matter halos around galaxies, influencing how galaxies cluster together. Furthermore, understanding these fluctuations helps scientists unravel the mysteries of dark energy, which is driving the accelerated expansion of the universe. Cosmic inflation, a theory proposing a rapid expansion of the universe shortly after the Big Bang, is intrinsically linked to quantum fluctuations. During this brief period, the tiny fluctuations were stretched across vast distances, seeding the universe with the initial variations needed for structure formation. This connection between quantum mechanics and cosmology highlights the unity of physical laws and the intricate dance between the very small and the very large. In conclusion, quantum fluctuations are not just abstract concepts confined to the realm of theoretical physics. They are the very foundation upon which our universe was built. By exploring these fluctuations, we gain a deeper appreciation for the complexities of the universe and the interconnectedness of various scientific disciplines. As we continue to probe the depths of quantum mechanics and cosmology, we uncover the profound mysteries that govern our existence and the universe at large. Chapter 6: The Philosophical Implications of Quantum Physics. Reality and Perception. The nature of reality and perception has long fascinated philosophers, scientists, and thinkers alike. In the realm of quantum physics, these concepts take on a new dimension, challenging our traditional understanding of the universe. What we perceive as reality is often a construct of our senses, influenced by our experiences, emotions, and biases. This interplay between the observer and the observed raises profound questions about the fabric of existence itself. Quantum mechanics posits that particles exist in a state of probability until they are observed, which suggests that reality is not as fixed as we might believe. The famous double-slit experiment exemplifies this phenomenon, where light behaves as both a wave and a particle, depending on whether it is being observed. This duality highlights the pivotal role of perception in shaping our understanding of the universe, leading to the conclusion that our observations can alter reality at a fundamental level. Moreover, the concept of reality is further complicated by the advancements in technology. Virtual reality, VR, and augmented reality, AR, blur the lines between what is real and what is simulated. These technologies allow us to experience environments that do not exist in the physical world, yet they can evoke real emotions and responses. As we become more immersed in these digital realms, the question arises: does our perception of reality change as we interact with these advancements? In addition, cultural and societal influences play a significant role in shaping our perception of reality. Different cultures have unique interpretations of existence, which can affect how individuals perceive their surroundings and experiences. This suggests that reality is not a universal constant but rather a subjective experience, colored by the lens through which we view the world. Understanding these diverse perceptions can deepen our appreciation for the complexity of human experience and the universe itself. Ultimately, the relationship between reality and perception is an ongoing exploration that intersects science, philosophy, and technology. As we delve deeper into the mysteries of the universe, we must remain open to the possibility that our understanding of reality is merely a reflection of our perceptions. The quantum frontier invites us to reconsider what we know and to embrace the unknown, reminding us that the quest for knowledge is as much about questioning as it is about discovery. The nature of time. Time, an elusive concept, has fascinated humans for centuries, intertwining with both philosophy and science. In our everyday lives, time dictates the rhythm of our existence. We plan our days around its relentless march. Yet, when we delve deeper into its nature, we find that time is not merely a simple progression from past to future but a complex and multifaceted phenomenon. The advent of quantum physics has radically altered our understanding of time, challenging the classical views that have dominated for so long. In classical physics, time is treated as an absolute entity, a constant that ticks uniformly regardless of external conditions. This perspective, rooted in the works of Newton, suggests that time flows the same for everyone, everywhere. However, the principles of quantum mechanics introduce a different narrative, one where time appears to be more relative and interconnected with the fabric of space. The implications of this shift are profound, suggesting that time may not be as linear and fixed as we once believed. One intriguing aspect of quantum theory is the notion of time as a dimension that can be affected by gravity and speed. Einstein's theory of relativity demonstrated that time can dilate, meaning it can stretch and compress based on the observer's velocity and the gravitational field surrounding them. This revelation has led to groundbreaking insights, such as the idea that time can behave differently for two observers moving at different speeds, creating a reality where their experiences of time diverge significantly. Moreover, recent advancements in quantum physics have sparked debates about the very beginning of time itself. The Big Bang theory posits that time as we know it began approximately 13.8 billion years ago, yet questions remain about what preceded this event, if anything at all. Some theorists propose that time may be cyclical or that it could exist in a state beyond our comprehension, challenging our understanding of existence and causality. Such discussions invite us to reconsider the boundaries of time and its role in the universe. Ultimately, the nature of time continues to elude definitive understanding, making it one of the most captivating subjects in contemporary science. As our technological capabilities advance, so too does our ability to explore these mysteries. The intersection of time with quantum mechanics not only reshapes our scientific paradigm but also invites us to ponder profound philosophical questions about reality, existence, and the universe itself. As we stand on the brink of new discoveries, the journey to comprehend the nature of time is just beginning. Free will and determinism. The debate between free will and determinism has intrigued philosophers and scientists alike for centuries. Free will posits that individuals can make choices independent of any preordained fate. On the other hand, determinism suggests that every event, including human actions, is the result of preceding causes that can be traced back through time. This philosophical dichotomy raises profound questions about our understanding of human agency and responsibility in a universe governed by physical laws. In the realm of quantum mechanics, the discussion takes an intriguing turn. The behaviour of particles at the quantum level appears to be fundamentally probabilistic, challenging the deterministic view held by classical physics. This unpredictability introduces a layer of complexity to the free will debate. If the universe is not entirely deterministic, does this open the door for genuine free will, or do quantum events still lead to a predetermined path when viewed on a larger scale? Neuroscience has also entered the fray, providing insights into how our brains make decisions. Studies have shown that our brains can initiate actions before we are consciously aware of them, suggesting that our sense of free will may be an illusion. This raises critical questions about moral responsibility and the extent to which we can be held accountable for our actions. If our decisions are influenced by unconscious processes, can we truly say we are free to choose? Moreover, cultural and societal influences further complicate the understanding of free will. The environment in which individuals are raised can shape their beliefs, desires, and ultimately their choices. This interplay between nature and nurture highlights the challenges in defining free will. Are we merely products of our upbringing and biological makeup, or do we possess the capacity to transcend these influences and make autonomous choices? Ultimately, the relationship between free will and determinism remains a complex and unresolved issue. While scientific advancements in quantum mechanics and neuroscience provide valuable perspectives, the philosophical implications continue to provoke thought and discussion. As we delve deeper into the mysteries of the universe, understanding the nature of free will may be one of the most significant challenges we face, prompting us to reflect on what it truly means to be human. Chapter 7. Challenges and Controversies in Quantum Physics. The measurement problem. The measurement problem in quantum mechanics arises from the peculiar behavior of particles at the quantum level. When a system is not being observed, it exists in a superposition of states, where it can simultaneously hold multiple possibilities. This leads to the fundamental question of how and when a quantum system transitions from this superposition to a single outcome upon measurement. The very act of measurement seems to influence the system, collapsing it into one specific state, which challenges our classical understanding of reality. Interpretations of quantum mechanics. Quantum mechanics, the science of the very small, has given rise to a variety of interpretations that seek to explain its counterintuitive implications. From the Copenhagen interpretation, which suggests that particles do not have definite states until measured, to the many-worlds interpretation, which proposes that every quantum event spawns a new universe, these theories challenge our understanding of reality. Each interpretation offers a unique perspective on how we comprehend the behavior of particles at the quantum level, leading to heated debates among physicists and philosophers alike. One of the most widely discussed interpretations is the Copenhagen interpretation, formulated by Niels Bohr and Werner Heisenberg in the early 20th century. This interpretation posits that quantum particles exist in a superposition of states until they are observed. The act of measurement collapses this superposition into a single outcome, suggesting that reality is not determined until it is observed. This idea raises profound questions about the nature of reality and the role of the observer in the quantum realm. In contrast, the many-worlds interpretation, introduced by Hugh Everett III, offers a radically different view. According to this theory, all possible outcomes of a quantum event occur, with each outcome existing in its own separate universe. This interpretation eliminates the need for wave function collapse, allowing for a deterministic universe where every possibility is realized. While it provides a cohesive framework for understanding quantum phenomena, it also leads to perplexing implications about the nature of existence and the infinite multiverse. Another notable interpretation is the de Broglie-Bohm theory, which introduces the concept of pilot waves guiding particles along deterministic paths. This interpretation maintains that particles have definite positions and velocities, contrasting sharply with the probabilistic nature of other interpretations. Advocates of this theory argue that it reconciles the strange behavior of quantum mechanics with a more intuitive understanding of reality, yet it remains less popular among mainstream physicists. The interpretations of quantum mechanics reflect the ongoing struggle to understand a universe that defies classical logic. As scientists continue to explore the quantum frontier, the dialogue surrounding these interpretations remains vibrant and essential. Each theory not only enriches our understanding of quantum mechanics but also challenges us to reconsider our fundamental notions of reality, observation, and existence itself. The future of quantum research. As we stand on the brink of a new era in science, quantum research is poised to revolutionize our understanding of the universe. The principles of quantum mechanics, which govern the behavior of particles at the smallest scales, are the foundation for innovations that could drastically alter technology. With advancements in quantum computing, researchers are beginning to unlock capabilities that were once thought to be the realm of science fiction. This burgeoning field promises not only to enhance computational power but also to tackle problems intractable for classical computers, thus opening new frontiers in data analysis and cryptography. Moreover, quantum research is not limited to computing. It extends to various applications including quantum communication and quantum sensing. Quantum communication leverages the principles of entanglement and superposition to create secure channels that are theoretically immune to eavesdropping. This could lead to the development of unhackable communication systems, ensuring the privacy of sensitive information in an increasingly digital world. Meanwhile, quantum sensors have the potential to significantly improve the precision of measurements in fields ranging from medicine to navigation, paving the way for breakthroughs in various scientific disciplines. The future of quantum research also holds promise for the development of new materials and energy solutions. By understanding the quantum properties of materials, scientists can engineer substances with unique characteristics that could lead to more efficient batteries, superconductors, and even new types of solar cells. These advancements could address some of the pressing challenges we face regarding energy consumption and sustainability. As researchers delve deeper into the quantum realm, the implications for material science could be profound, leading us towards a greener future. International collaboration and investment in quantum research are also crucial for driving progress in this field. Countries around the world are recognizing the strategic importance of quantum technologies and are increasing funding for research initiatives. Collaborative efforts between academia, industry, and governments can accelerate discoveries and facilitate the practical application of quantum theories. As more talent enters the field, we can expect an influx of innovative ideas that will further propel our understanding and utilization of quantum phenomena. In conclusion, the future of quantum research is bright and brimming with potential. As we continue to explore the mysteries of the quantum world, we stand to gain insights that could reshape our technological landscape and enhance our quality of life. The journey into the quantum frontier is just beginning, and the discoveries that lie ahead may well redefine the boundaries of science and technology as we know them. Chapter 8. Pioneers of Quantum Theory. Max Planck and the birth of quantum theory. Max Planck, a German physicist, is often regarded as the father of quantum theory. In the late 19th century, he was faced with a problem that had baffled scientists: the challenge of black body radiation. Classical physics could not explain why objects emitted radiation in certain patterns when heated, leading to what was known as the ultraviolet catastrophe. To resolve this, Planck proposed a revolutionary idea: that energy is quantized and can only be emitted or absorbed in discrete amounts, or quanta. This radical departure from classical thought laid the groundwork for modern physics. Planck introduced the concept of the quantum of action, now known as Planck's constant, which is fundamental in the realm of quantum mechanics. By quantifying energy in this manner, he was able to derive a formula that accurately described black body radiation, which matched experimental results perfectly. This breakthrough not only resolved the inconsistencies of classical theories but also opened the door to a new understanding of the physical universe. Planck's work marked a pivotal shift in scientific thought, suggesting that at a microscopic level, the rules governing energy and matter were vastly different from those observed in everyday life. In 1900, Planck presented his findings at a conference, but the implications of his work were not immediately recognized. Many in the scientific community were hesitant to abandon the well-established principles of classical physics. However, as other physicists began to build upon Planck's ideas, the acceptance of quantum theory grew. Notably, Albert Einstein later adopted Planck's concepts to explain the photoelectric effect, further solidifying the quantum framework that would redefine scientific inquiry. The evolution of quantum theory during the early 20th century was not without controversy. As scientists delved deeper into the quantum realm, they encountered perplexing phenomena that challenged their understanding of reality. Concepts such as wave-particle duality and uncertainty began to emerge, leading to debates about the nature of existence itself. Planck's initial insights into quantization were the first steps into this bewildering landscape, where particles could exhibit both wave-like and particle-like properties depending on the circumstances of their observation. Today, Max Planck's contributions are celebrated not only for their scientific significance but also for the philosophical questions they raise about the nature of reality. Quantum theory has since evolved into a foundational pillar of modern physics, influencing various fields from chemistry to technology. Planck's legacy endures, reminding us that the journey of scientific discovery often begins with a single, transformative idea that challenges our perception of the universe. Albert Einstein and quantum disputes. Albert Einstein, one of the most celebrated physicists in history, is often associated with groundbreaking theories that reshaped our understanding of the universe. However, his relationship with quantum mechanics was anything but straightforward. While he contributed significantly to the early development of quantum theory, his later years were marked by profound disputes with the field's emerging principles, particularly the concept of quantum entanglement. Einstein famously referred to this phenomenon as spooky action at a distance, expressing his discomfort with the idea that particles could be instantaneously connected across vast distances without any apparent mechanism. Einstein's primary contention with quantum mechanics revolved around its inherent randomness and the probabilistic nature of its predictions. He believed that a complete theory should not rely on chance but rather offer deterministic outcomes. This perspective led to the famous debate between Einstein and Niels Bohr, a leading proponent of quantum theory. Their correspondence and public debates laid the groundwork for many philosophical discussions about the nature of reality and the limits of scientific knowledge. The disagreements between Einstein and quantum physicists were not merely academic. They reflected a deeper philosophical divide regarding the interpretation of scientific theories. While Bohr and his contemporaries embraced the strange implications of quantum mechanics, Einstein sought a more intuitive understanding of the universe. He posited that there must be hidden variables, yet to be discovered, that would restore determinism to the quantum realm. This idea spurred numerous debates and experiments, notably the Bell's theorem, which would later challenge Einstein's views. Despite his skepticism, Einstein's critiques played a crucial role in shaping the trajectory of quantum physics. His concerns prompted physicists to refine their theories and explore the implications of entanglement and non-locality more rigorously. Over time, many of the phenomena that Einstein questioned have been experimentally validated, yet debates about the interpretation of quantum mechanics continue to this day. This ongoing discourse highlights the complexity and richness of scientific inquiry. In retrospect, Einstein's legacy in the realm of quantum mechanics is paradoxical. His initial contributions helped lay the foundation for the field, while his later disagreements sparked critical discussions that continue to influence modern physics. Understanding these quantum disputes not only provides insight into Einstein's character but also illustrates the evolving nature of scientific thought, where even the greatest minds can grapple with ideas that challenge their beliefs. Niels Bohr and the Copenhagen interpretation. Niels Bohr, a pioneering figure in the field of quantum mechanics, played a crucial role in shaping our understanding of atomic structure and the behavior of subatomic particles. His work laid the foundation for what is now known as the Copenhagen interpretation, a philosophical framework that emerged in the early 20th century. This interpretation seeks to explain the strange and often counterintuitive nature of quantum phenomena, where particles can exist in multiple states until observed. At the heart of the Copenhagen interpretation is the idea of wave-particle duality, which posits that particles, such as electrons, can exhibit properties of both waves and particles depending on how they are measured. Bohr famously articulated this concept, suggesting that the act of measurement itself plays a fundamental role in determining the state of a quantum system. This challenges our classical intuitions about reality, leading to profound implications for our understanding of the universe. Bohr's collaboration with fellow physicists, including Werner Heisenberg, further refined the Copenhagen interpretation, introducing concepts like complementarity. This principle asserts that different experimental setups can reveal different aspects of a quantum system, highlighting the limits of classical descriptions. As a result, Bohr suggested that a complete understanding of quantum mechanics requires embracing its inherent uncertainties instead of trying to impose deterministic views. The philosophical implications of Bohr's ideas extend beyond physics, influencing various fields, including philosophy, psychology, and even art. The notion that reality is not as straightforward as it seems invites a re-evaluation of how we perceive the world around us. Bohr's work encourages a dialogue between science and philosophy, fostering an appreciation for the complexities and mysteries that underpin our existence. In conclusion, Niels Bohr's contributions to the Copenhagen interpretation have profoundly shaped our understanding of quantum mechanics and the nature of reality. His insights challenge us to reconsider the principles that govern our universe, illustrating that at the quantum level, certainty is often replaced by probability. As we continue to explore the quantum frontier, Bohr's legacy remains a guiding light, illuminating the path to deeper knowledge and understanding of the cosmos. Chapter 9. The Future of Quantum Exploration. Emerging Technologies and Innovations. Emerging technologies and innovations are shaping our understanding of the universe in unprecedented ways. Advances in quantum computing, for instance, are enabling scientists to solve complex problems that were previously thought to be insurmountable. These breakthroughs not only enhance our computational capabilities but also open new avenues for research in various scientific fields, including physics, chemistry, and materials science. One of the most promising developments in recent years is the rise of artificial intelligence, AI, and machine learning. These technologies are being employed to analyze vast amounts of data generated by scientific experiments and observations. By identifying patterns and making predictions, AI is helping researchers to accelerate discoveries and gain deeper insights into the fundamental workings of the universe. In addition to AI, the field of nanotechnology is also making significant strides. By manipulating matter at the atomic and molecular levels, scientists are creating materials with extraordinary properties. This not only revolutionizes our understanding of material science but also has practical applications in various industries, from medicine to electronics, paving the way for innovative solutions to complex problems. Moreover, the integration of renewable energy technologies is transforming how we approach sustainability and environmental challenges. Innovations such as advanced solar cells, energy storage systems, and smart grids are helping to harness clean energy more efficiently. These advancements are essential for reducing our carbon footprint and ensuring a sustainable future for generations to come. Finally, the exploration of space is entering a new era with the advent of private space travel and innovative spacecraft technologies. Companies are developing reusable rockets and advanced propulsion systems that promise to make space exploration more accessible. This shift not only fuels scientific curiosity but also encourages international collaboration in the quest to understand our universe better. The quest for a unified theory. The quest for a unified theory has captivated scientists for generations, representing a profound ambition to explain the fundamental forces of nature within a single framework. This search is not merely an academic exercise. It embodies humanity's desire to understand the universe at its most basic level. The challenge lies in the fact that the four fundamental forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, operate under different principles and scales, complicating efforts to unify them into one cohesive theory. Historically, significant strides have been made in this pursuit. Albert Einstein's theory of general relativity provided a groundbreaking understanding of gravity, while James Clerk Maxwell's equations beautifully combined electricity and magnetism. However, the Standard Model of particle physics, which successfully describes the electromagnetic, weak, and strong forces, leaves out gravity. This gap has led to an ongoing search for a theory of everything that can reconcile these discrepancies and provide a more comprehensive understanding of our universe. In recent years, string theory has emerged as a promising candidate for this elusive unified theory. By proposing that the fundamental particles are not point-like but rather tiny vibrating strings, it offers a framework that can potentially incorporate all four forces. However, string theory remains largely theoretical and untested, leading to debates within the scientific community about its validity and applicability. The complexity of the mathematics involved also poses a barrier to its acceptance, as many scientists seek more empirically grounded theories. Another intriguing approach is loop quantum gravity, which attempts to quantize gravity without requiring the extra dimensions proposed by string theory. This theory posits that space-time itself has a discrete structure at the Planck scale, fundamentally altering our perception of reality. While loop quantum gravity has made some progress, it has yet to achieve the same level of consensus or experimental validation as the Standard Model. The quest for a unified theory not only fuels scientific discourse but also inspires philosophical contemplation about the nature of reality. As researchers continue to explore the depths of quantum mechanics and cosmology, each new discovery brings us closer to understanding the universe's mysteries. Although we may not yet have a definitive answer, the journey itself is a testament to human curiosity and the relentless pursuit of knowledge. Quantum physics and the search for extraterrestrial life. Quantum physics, with its perplexing principles and counterintuitive concepts, opens new avenues for understanding the universe, particularly in the quest for extraterrestrial life. The fundamental tenets of quantum mechanics challenge our traditional views of reality, leading scientists to question not just what exists beyond our planet, but how those entities might exist and interact with the cosmos. The exploration of quantum phenomena might help us uncover signals or signatures indicative of life elsewhere in the universe, as we delve deeper into the mysteries of quantum entanglement and superposition. One of the most intriguing aspects of quantum physics is its application in the realm of communication. Quantum entanglement, which describes how particles can be interconnected in ways that transcend classical physics, could potentially allow for instantaneous communication over vast distances. This concept has led researchers to consider whether advanced extraterrestrial civilizations could harness such technology, enabling them to communicate across the cosmos in ways that we have yet to fully comprehend. As we develop our understanding of these phenomena, we might also enhance our own capabilities in seeking out life beyond Earth. Moreover, the search for extraterrestrial intelligence, SETI, has begun to incorporate quantum theories into its methodologies. Scientists are exploring the possibility that advanced civilizations may use quantum technologies to transmit signals that are disguised or difficult to detect by our conventional instruments. This paradigm shift in thinking encourages a more nuanced approach to the signals we receive from space, prompting researchers to consider not just the content of these signals, but the underlying quantum processes that could shape them. As we venture further into the quantum frontier, the implications for astrobiology become profound. The characteristics of life as we understand them might not be applicable to extraterrestrial organisms, which could exist in states or forms we cannot yet imagine. Quantum biology, a burgeoning field, examines how quantum mechanics might play a role in the processes of life, suggesting that the very essence of living systems could be intertwined with quantum phenomena. This perspective broadens the horizons of what we consider possible in the search for life beyond our planet. Ultimately, the intersection of quantum physics and the search for extraterrestrial life invites us to rethink our place in the universe. As we develop new technologies and refine our understanding of quantum mechanics, we may uncover evidence of life that challenges our assumptions about biology and intelligence. The quest is not merely about finding aliens. It is about understanding the fundamental nature of existence itself and our own potential in the vast, mysterious cosmos. Chapter 10. Conclusion: The Quantum Frontier. Reflecting on the journey. Reflecting on the journey through the vast realms of quantum physics, we find ourselves at the intersection of imagination and reality. Each step taken in this exploration has unveiled deeper layers of understanding, challenging our preconceived notions of the universe. As we delve into the minutiae of subatomic particles and their behaviors, we are reminded of the intricate tapestry that makes up the cosmos, where even the smallest actions have profound implications. The advancements in quantum technology have not only transformed scientific research but have also begun to impact our daily lives. From quantum computing to quantum cryptography, these innovations are paving the way for a future that was once merely theoretical. As we reflect on the milestones achieved, it becomes evident that this journey is not just about the discoveries made, but also about the questions that continue to arise, pushing us further into the unknown. Moreover, the collaborative spirit that has characterized this journey cannot be overlooked. Scientists from diverse backgrounds have come together, sharing their insights and expertise to enhance our understanding of quantum mechanics. This unity has fostered an environment where ideas can flourish, demonstrating that the pursuit of knowledge is a collective endeavor that transcends borders and disciplines. As we pause to reflect, we also recognize the philosophical implications that arise from our findings. The very fabric of reality appears to be more interconnected and less deterministic than previously thought. This realization invites us to reconsider our place in the universe, suggesting that we are not merely observers but active participants in a grand cosmic dance that continues to evolve. Looking ahead, the journey through the quantum frontier remains as exhilarating as ever. With each discovery, we unearth new possibilities and challenges that beckon us to advance our understanding further. As we embrace the mysteries that lie ahead, we do so with a sense of wonder, eager to explore the depths of the universe and the potential that quantum science holds for humanity's future. The ongoing exploration of the universe. The universe remains one of the most fascinating realms of exploration for humanity. With each passing year, advances in technology allow us to observe deeper into space and uncover mysteries that have long eluded our understanding. From telescopes that gaze into the farthest reaches of the cosmos to satellites that map the cosmic microwave background, our tools are becoming increasingly sophisticated. This relentless pursuit of knowledge fuels both scientific inquiry and the human imagination, pushing us to ponder our place in the vast expanse of the universe. Recent missions have significantly enhanced our comprehension of celestial phenomena. For instance, the Hubble Space Telescope has provided breathtaking images and invaluable data, revealing the dynamics of distant galaxies and the birth of stars. In addition, rovers like Perseverance on Mars are directly investigating the possibility of past life on other planets, showcasing how exploration is not limited to our own world. Every discovery leads to new questions, urging scientists to delve further into the cosmic unknown. The study of dark matter and dark energy is another frontier that challenges our understanding of the universe. Together, these phenomena constitute a substantial portion of the universe's mass-energy content, yet remain largely invisible and undetectable. Scientists are tirelessly working to unlock the secrets behind them, employing both theoretical models and experimental approaches. This ongoing research exemplifies the interplay between observation and theory, driving progress in our quest to comprehend the very fabric of reality. Moreover, the exploration of exoplanets has opened a new chapter in the search for extraterrestrial life. The Kepler Space Telescope and its successors have identified thousands of planets outside our solar system, some situated in the habitable zone where conditions may support life. This tantalizing possibility has sparked a renewed interest in astrobiology, prompting scientists to investigate not only the chemical conditions necessary for life but also the potential for diverse ecosystems beyond Earth. In conclusion, the The ongoing exploration of the universe is a testament to human curiosity and ingenuity. Each discovery, whether it be the observation of a distant galaxy or the analysis of a Martian rock, brings us closer to understanding the cosmos and our place within it. As technology continues to evolve, so too will our ability to explore and uncover the profound mysteries that lie beyond our planet, ensuring that the quest for knowledge remains an enduring legacy of humanity. Inspiring future generations in science and technology. Inspiring future generations in science and technology is essential for the advancement of society. It begins with nurturing curiosity in young minds, encouraging them to ask questions about the world around them. The quest for knowledge should be presented as an exciting journey rather than a daunting task. By fostering an environment where exploration is welcomed, we can empower future innovators to pursue their passions in these vital fields. Educational institutions play a critical role in shaping the interests of students. By integrating hands-on learning experiences, such as science fairs and technology workshops, schools can ignite a spark of interest in young learners. Collaborations with local science centers and technology companies can provide students with real-world insights, making abstract concepts more tangible. This practical exposure can transform students' understanding and inspire them to envision a future where they contribute to groundbreaking discoveries. Mentorship is another vital component in inspiring the next generation. By connecting students with professionals in the fields of science and technology, we can offer them guidance and support. Mentors can share their experiences, challenges, and triumphs, providing a roadmap for students to follow. This personal connection can motivate young individuals to pursue careers in these fields and instill a sense of responsibility to pass on their knowledge to others in the future. Furthermore, the role of technology in education cannot be underestimated. With the advent of online resources and interactive platforms, students have unprecedented access to information and learning tools. Virtual labs and simulation software allow them to experiment and innovate in a safe environment. By harnessing these technologies, educators can create dynamic learning experiences that not only engage students but also prepare them for the complexities of modern scientific and technological landscapes. In conclusion, inspiring future generations in science and technology requires a multifaceted approach that includes curiosity, hands-on experiences, mentorship, and the innovative use of technology. It is a collective responsibility to ensure that the next generation is equipped with the knowledge and skills to tackle the challenges of tomorrow. By fostering a passion for these fields, we can pave the way for a brighter future, driven by the creativity and ingenuity of our youth.